apply the momentum operator to that side. So we're going to take minus I h bar ddx of b e to the minus I kx. What are we going to get as a result of that? Dead. Sorry. So what if we apply the momentum operator to b e to the minus I kx? What happens then? Yeah, you get minus h bar k b e to the minus I kx. So we get minus h bar k times the original psi. So is that an eigenfunction of the momentum operator? Well, p psi is minus h bar k psi. K is just a k, h bar k is just a number, right? For a given value of k, it can be any value of k we like, but for a given value of k, minus h bar k is just a number, so is psi equals b e to the minus I kx an eigenfunction of the momentum operator? Sure is, yeah. So our conclusion here is b e to the minus I kx is a state having definite momentum minus h bar k. And what's its energy? Yeah, what's the energy of that state?
Again, p squared by 2m.
It's again p squared over 2m. Yeah, if I could put e to the minus I kx here, I would get h bar squared minus k the quantity squared, which would still be h bar squared k squared over 2m. So it's still p squared over 2m. Well, this makes sense. In classical physics too, if I have a particle moving with some momentum p, and another particle moving with some momentum minus that, they both have the same kinetic energy. They both have the same value for p squared over 2m. So all this is saying is you can have a particle moving to the left or moving to the right, and if the momentum is the same, they still have the same energy, even though their momentum is equal and opposite. So what about a e to the I kx plus b e to the minus kx? Is that a state of definite momentum? Does that system have definite momentum? Not a system. If I have a particle whose wave function is, a free particle whose wave function is a e to the I kx plus b e to the minus I kx, which it's certainly allowed to have, does that have definite momentum or not? Well, what happens if I hit it with p? P psi is minus I h bar ddx of a e to the I kx plus b e to the minus I kx. What's that give me? What do I get for the first term when I hit a e to the I kx with minus h bar ddx? So I get h bar k a e to the I kx. What about the second term? Minus h bar k b e to the minus I kx. Is that a number times a e to the I kx plus b e to the minus I kx? It is not.
Because it is a linear combination.
Exactly, that's right. That's not an eigenfunction of the momentum operator. It's not a state having definite momentum because it's a mixture of states having different momentum. It's a mixture of states having different momentum. So if I measure the momentum, what values could I get? Not A or B, that's the amplitude. I could either get h bar k or minus h bar k, just like we've seen before. If you mix states that have definite values of something like the energy, right? When we mix states of a harmonic oscillator, if we mix, like, you remember you had a problem where you had 3/5 psi naught plus 4/5 psi 1, then if you measured the energy, you were either going to get E naught or E1, and the probability of E naught was 3/5 squared, 9/25, and the probability of E1 was 4/5 squared, or 16/25. So you were going to get one or the other, no other possibility, and the probability was the coefficient squared. Well here, even though this sucker isn't normalizable, if we have a combination like this, we could still impose a squared plus b squared equals 1 in order to get an interpretation in terms of the probabilities here. So in any case, the probability of getting h bar k would be proportional to a's absolute square. The probability of getting minus h bar k would be proportional to the absolute square of b. And if we make them add up to 1, then we could make it such that a squared represented the probability of getting h bar k and b squared representing the probability of getting minus h bar k. So how would I make it a 50-50 mix? If I want a 50-50 mix, what do I do? 50% chance of getting h bar k, 50% chance of getting minus h bar k. Well, c squared, if I think it was like c1 psi 1 plus c2 psi 2, then c1 squared is the probability of getting psi 1, and c2 squared is the probability of getting the eigenvalue for psi 2, right? So if c1 squared is 2, what's c1? I'm sorry, c1 squared is a half, not 2. c1 squared is a half. 1 over root 2 would be the coefficient, right? So if I wanted a 50-50 mix of h bar k and minus h bar k, I could do it as 1 over root 2 e to the I kx plus e to the minus I kx, and that would say 50-50 probability of getting either h bar k or minus h bar k. I could also put a minus sign in there, it'd still be 50-50 because it's the absolute squares of the coefficients that would matter. I could put a plus e to the I phi, where phi is some arbitrary phase constant. I could throw that in there as well. Remember you did a homework problem where you showed that the relative phases actually does matter if you're creating a superposition like that. So we've concluded this is not a state of definite momentum. How about energy? Is it a state of definite energy? Is it a state of definite energy? Well, let's find out. Maybe you can immediately see it, but if I want to know the energy, if I want to find out if it's a state of energy, what operator do I hit it with? What's the energy operator generically called? The Hamiltonian. So I want to hit it with H psi. But in this case, the Hamiltonian operator is just which operator? The kinetic energy operator. But that's 1 over 2m times the p squared operator minus h bar squared d squared dx squared. But what does p squared apply to either one of these states? P for this state gives h bar k. P for this state gives minus h bar k. So what does p squared give for either one of them? Yeah, h bar squared k squared. Which you can also get by taking the second derivative with respect to x. You can get it the same way. H bar squared k squared over 2m times psi. So, yes. It does have definite energy. So, well, it's quantum mechanics, so things can be weird. You can have a particle which is a mixture of left momentum and right momentum. And as long as the values of left momentum and right momentum are the same, then it will have a definite energy, but it won't have a definite momentum. If you measure the energy, you're going to get h bar squared k squared over 2m. But if you measure the momentum, you might get plus h bar k, you might get minus h bar k. And the sizes of a and b, or really a squared and b squared, determine what's the probability of getting plus h bar k, what's the probability of getting minus h bar k. So that doesn't happen in classical physics. You can't have a classical particle where it's got a definite kinetic energy, it's definitely moving at some speed, but it might be moving to the left, it might be moving to the right. It's in a superposition, right? I mean, have you ever driven a car where you can go both north and south at the same time? I haven't. It'd be cool, but I haven't driven such a car. But in quantum mechanics, a quantum car could do that in some weird sense. Quantum car, that's right. The new Ford Quantum.
You get to so many other places so much faster. They just
That's
hurry up
right.
and do those things.
Yeah, there you go. Yes. Well, yeah, the problem is, it's like, yeah, so it's Thanksgiving, do I visit my parents or do I visit my wife's parents? So, we get in our quantum car and we go both places, but the problem is that, the wave function is going to collapse, and so we don't actually end up being observed in both places, which kind of sucks. We gave it our best quantum effort. So.
At least you can tunnel through a traffic jam.
Yeah, you could tunnel through a traffic jam. That's right. Yes. If you wait long enough. Yeah. Okay. Any questions? Time for more quantum weirdness, which you've seen before. You've seen this in Physics 280. But it's time for a reminder. Let's attach the time dependence. So, where did I put it? There we go. Let's take AE to the IKX. If psi of x is AE to the IKX, then the rule for constructing psi of xt is to attach e to the minus I et over h bar, right? If you've written psi as a sum of eigenfunctions of the Hamiltonian, then the general wave function psi of x and t is obtained by attaching e to the minus I et over h bar to each piece in the superposition. Here there's only one piece. There's only one eigenfunction of the Hamiltonian in the wave function, namely e to the ikx. So I attach the energy of that state, e to the minus I et over h bar to it. But E here is h bar squared k squared over 2m. So the full time-dependent wave function here is a e to the I kx minus h bar k squared over 2m t. When I tack on e to the minus I et over h bar, and then use the fact that the exponential, complex exponentials do the same thing real exponentials do. In other words, if you multiply two complex exponentials together, you can make it a single complex exponential whose exponent is the sum of the exponents of the two guys you multiply together there. That's a traveling wave, right? That's a traveling wave. Which way is it going? Yeah, to the right. This is a traveling wave heading to the right because the sign of the t term is opposite the sign of the x term there. So as x increases, as t increases, this thing is moving to the right. I made it a e to the minus ikx, I'm just going to call it a now instead of b. Psi of xt would be a e to the minus ikx minus h bar k squared over 2m t. Actually, let me factor it the way I did before. It'll be e to the minus I kx plus h bar k squared over 2m times t. And I multiply by e to the minus I dt over h bar. Which way is that wave headed? That's headed to the left because it's got the form where the sign over here is the same for the t in the next term. How fast are these waves traveling? Take the top one here. I rewrite e to the I kx minus h bar k squared over 2m times t. I rewrite that as a e to the I k. So I factor k outside of it and say this is e to the I k x minus h bar k over 2m times t. And now I've written it in the form of Ea e to the I k x minus dt. I've written it as a function of x minus vt so that I can read off the speed from that. So the crests of the wave the phase speed is what here? Is h bar k over 2m. The coefficient of t, when I write it as a function of x minus vt, is the speed the wave is traveling, the crest of the wave we're traveling. So it's moving at speed h bar k over 2m. What's h bar k? The momentum, p. So it's moving at speed p over 2m. If this is a classical particle, how fast is it moving? How fast is it moving? How do you get the speed from the momentum in classical physics? Yeah, p is mv. Right? P is mv in classical physics, so v is p over m in classical physics. So this is half v sub cl, where the v sub cl is the classical speed of the wave. V sub cl here is p over m equals speed of a classical particle with momentum p. A classical particle with momentum p is p over m, but our wave appears to be traveling at half that speed. This term down here, one like this, would represent a wave going to the left at half the classical speed. So in either case, the particle, it would appear at first, seems to be going only at half the classical speed. The wave crests are only moving half as fast as the classical particle would for the same amount of momentum, which seems kind of strange. I mean, on one level you say, oh, it's quantum mechanics, so we don't expect the perfect correspondence to classical physics. But on the other hand, that would be rather strange if you had this whole factor of 2 like that. So what's the resolution? Going back to those halcyon days of physics 280, and maybe physical chemistry. Did you guys ever do anything like this in physical chemistry? chemistry? You may not, because this is more kind of theoretical stuff, and it's not of such direct interest to a chemist. So, how do we get around this? Do you remember?
The group velocity.
Yeah, we have to worry about, this is what we call the phase velocity. It's how fast the crests of the wave are moving. But, if you make a wave out of a combination of waves having different momentum, you can produce what we call a wave packet. And the envelope of the wave packet travels at what we call the group velocity. And when we find the group velocity for a free particle, that is equal to the classical velocity. It's equal to just p over m in that case. And we're gonna show that, but I'm going to show an applet, a Java applet that I found on this really nice website that you should go to, because there's all kinds of great stuff here. So I'll put this URL down. There's all kinds of demonstrations of physics and engineering and math concepts that this guy has written as these Java applets. And gosh, I'm going to be making use of these things for showing you guys stuff in class. The address, but you should just look on your own, it's www.falstad.com. falstad.com/mathphysics.html.
Yeah, for one thing, I thought you said math, physics.
Yeah, well, could be.
Would be a bit more fun, I think.
Yeah. So now I'm going to, actually I'm trusting that this computer has Java on it. I actually haven't tested that. I'm going to trust that it will actually pull up this dispersion applet, otherwise I'm going to download. Oh, there it is. Oh, well, what the hell is that? That's not. That's coupled oscillators. I must have clicked the wrong one. Okay. But it does have Java. That's the good thing. Dispersion applet. Yeah, I hit the coupled oscillator applet. There we go. All right. Let me stop this thing. So, what I'm going to do is, I'll unstop it for a second. What I'm going to do is to, you can't see it. I can see it. Screen to life. And I better hit some lights.
Oh, yes.
There we go. No, you're not going to sleep because this is good, exciting stuff. Except maybe you will, because you were kind of falling asleep there before. No matter how exciting it is, you're going to find a way to fall asleep. All right. So,
oh yes, it's remember this, it's
yeah, you guys in 280 you made a Mathematica notebook that did something a lot like this. So,
it's also the fact that it was a physical phenomenon of beats, actually.
yeah, they're right, just beats are involved here. So, on the top and the middle, we've got two waves which have slightly different wavelengths. Not quite the same wavelength. Now, sound in air or light in a vacuum is what we call non-dispersive. In other words, consider light in a vacuum. The speed of light in a vacuum is independent of the wavelength. So no matter what the wavelength is, the waves travel at the same speed. And that's called a non-dispersive situation. But there are other waves where the speed of the wave does depend on the wavelength. And that's what we're going to look at here. So I'm going to make it so that the speed of wave 1 is a little bit less than the speed of wave 2. I think that's what I want here. And get it going there. Yep, okay. So I will stop it, like so. So, well, okay, so let me make it a bigger difference at first here. So what I want you to do first is notice when you look up top, restart. Okay. No. That's not what I meant. Okay, but if I unstop it, here we go. Yay. Oh, isn't that cute? Okay, they're starting out. So that, oh, that's even better. Okay. So you can see that the wave on the bottom, which is a shorter wavelength than the wave on the top, is moving faster than the wave on the top is. And so the middle wave is moving faster than the top wave. They're both pure sinusoids. On the bottom is their sum. So point by point you add them together. And you see what results. And so if I stop it again, you can see that in this region right here, the two waves are very nearly in phase with one another. In other words, troughs line up with troughs, crests line up with crests, so that when I add the two waves together, I get an amplitude which is about double that of either wave alone. However, because their wavelengths are different, they keep going in and out of phase with one another as you move along the x-axis. Over here, now they've gotten to about 180 degrees out of phase with one another. This trough on the middle wave nearly lines up with a crest on the top wave. And so as a result, when you add the two together, they almost cancel out there. And that pattern keeps repeating. Because the wavelengths are different, they go from in phase to out of phase to in phase to out of phase over and over again. And so the amplitude of the two waves added together goes up and down and up and down and up and down. And furthermore, if you then let it fly, like so, you can see that, of course, where they're added together, the whole pattern moves. But not only that, if we look very closely, so I'm going to slow down the simulation speed here.
Doesn't a wave envelope move faster than normal?
Not always. It depends. It depends on the dispersion relation. It depends on exactly how the speed depends on wavelength. What we can see here is, notice that the envelope, and by that I mean the overall amplitude of the overlapping pattern between the waves, the envelope here is not moving at the same speed as the crests inside the envelope. So you can see here that what we call the group velocity, which is how one of these packets of going from minimum to maximum amplitude and back again to minimum, one of these packets is moving along at the speed that I'm duplicating with my hand right here. That's not the same as the speed at which the little waves inside the envelope are moving. The phase velocity is how fast the individual crests are traveling inside the envelope. The group velocity is how fast the envelope itself is moving. So in the case I have here, which is faster, the group velocity or the phase velocity? Yeah, it's the group velocity, right? Because notice, if I follow the edge of the envelope here, it's moving faster than this crest is back here. Notice that the distance between my fingers is getting bigger over time. So this is a case where the group velocity is greater than the phase velocity. And that's because of the way that I've arranged the speeds here. But if I play around with it, I can, well, let's see if I try to match the frequencies. I'm sorry, I don't want to match the frequencies. If I try to match their speeds, then I can get a situation, I don't know how well I'll be able to do it, but if I match their speeds, oh no, that's okay, I like that again, that's right. So if I match their speeds with one another, and let's pick it up a little bit with the board. Oh, and don't say stop every time. By the way, I hate mouse pads. I hate pads. I like mice much better. Anyway, there we go. So if I can completely match their speeds, then the group and phase velocity should be exactly equal to one another. So I'm getting there. I'm not quite there, but if I perfectly were able to match them, and here I'm awfully close to that, then the crests and the envelopes would be going the same speed. I'm not quite there, which is why there's this wiggity happening there. But if I perfectly match them, everybody will travel together. So in a non-dispersive medium, if the phase speed is independent of wavelength, then the group velocity and the phase velocity are exactly the same. But, you know, oh, loads of fun. Let me drop the speed of the shorter wavelength wave to less than the longer wavelength wave. I can even, if I get extreme enough, I can even have the group velocity backwards. I can have the groups moving opposite the direction of the individual crests in a funky situation like that. But here, notice I've got the shorter wavelength wave is moving a little bit slower than the longer wavelength wave. Shorter wavelength speed 2 is a little bit less than longer wavelength speed 1. So which one is faster now, the group velocity or the phase velocity? Well, notice here, if I follow along, this distance, if I follow along this, I'm not doing very good. My finger wants to move too fast here. It's decreasing. The distance between my fingers, is decreasing here as I try to follow a crest and the edge of an envelope. So here, the phase velocity is faster than the group velocity. The crests inside are traveling faster than the envelope is. Whereas if I flip it and make the shorter wavelength move faster than the longer wavelength, then I get the other situation where the phase velocity is less than the group velocity. So it can go either way depending on the details. Okay, so I highly recommend going to that site and playing with this applet yourself. It's a great way to hypnotize yourself and to have loads of fun. So let's talk about that, shall we? Let's apply that to the situation here. There's a lengthy derivation in your book that I strongly encourage you to look at, but that I don't want to go through here because, well, it's a lengthy derivation. And in Physics 280, I did this sort of qualitative thing where I showed mathematically if you add two waves together and you're moving slightly different speeds, then you find how to get the group velocity versus the phase velocity from the group velocity is basically related to the difference in the phase speeds and the, well, anyway, whatever. What am I trying to say here? I'm feeling inarticulate. In 280, I literally added two waves together and showed how to get the group and phase velocities from that. And then we made a plausibility argument that it turns out that the group velocity is d omega dk and the phase velocity is omega over k. In your book, there is a more rigorous proof that the group velocity is d omega dk using Fourier transforms and so forth. I'm not going to go through that in here, but I will state the result basically. So, first, let's talk about how you can make a group in general, a wave packet in other words. So, going back to our, actually, do I want to do that? Maybe I should, I'm trying to figure out how I want to do this. Maybe what I'll do is, first I'll just talk about in general terms. So here I've made the, not that you can see them anymore, but I've made the wave packets by adding two waves together, slightly different wavelengths. And in general, if you want to make a wave packet that doesn't repeat forever, you know, here the wave packet itself goes back higher and lower amplitude all the way to plus and minus infinity, if I let these waves wiggle all the way to plus and minus infinity. If you want a finite length wave packet, if you want a wave packet that does something like, it's essentially 0, but then it does something like that before turning to 0 again forever, what you have to do is have a continuous distribution of frequencies that you add together that are all in some narrow range. And then you can get so that everything cancels out except in some small region. And you can talk about how fast does this single packet of waves travel compared to the speed of the crests inside of it. And what you find in the end is that the group velocity is d omega dk evaluated at k equals k naught where k naught is the value of k which, in some sense, contributes most strongly to building the packet. Building the wave packet. So I have a bunch of waves of the form e to the I kx minus omega t. So omega is the radian frequency of the waves, and k is what we call the spatial frequency of the waves. So if I have e to the I kx minus omega t, how is the wavelength of the wave related to k? If I have e to the I kx minus omega t, how is the wavelength related to k? What if I had just sine kx? That's a sinusoid, right? Sine kx. If I plotted that versus x, that's just a sine function. Lambda is the peak-to-peak distance. Yeah, it's 2 pi over k, right? Because the sine of k x plus lambda has to equal the sine of kx. If I've gone through one wavelength, I have to be back where I started again. So the sine of kx plus lambda is the same as the sine of kx, but the sine of kx plus 2 pi, if I've gone through one wavelength, I've gone through 2 pi a phase, the sine of kx plus 2 pi is also certainly the sine of kx. So we say, okay, then k lambda has to equal 2 pi when I've gone through one wavelength, and therefore k is 2 pi over lambda. And we call that the spatial frequency. K is the spatial frequency, spatial radian frequency if you like, but we should just say the spatial frequency. It's 2 pi over the wavelength. Its units are going to be radians per meter. Radians per meter, because wavelength is meters. So similarly, well, what do we usually give as the symbol for the temporal period, the time over which a disturbance repeats itself, a sinusoidal disturbance repeats itself? The temporal period, we usually give that the symbol capital T, right? And how is omega related to capital T? T over 2 pi. 2 pi over T. Yeah, 2 pi over T. So T is seconds, omega is radians per second, 2 pi over T. So if I have e to the I kx minus omega t, then k is 2 pi over lambda and omega is 2 pi over capital T. And if I want to write this in the form of x minus dt, a function of x minus dt, I'll write e to the I k x minus omega over k times t. phase speed, the speed at which the crests of the wave are moving. That's a sinusoidal wave, because e to the I kx minus omega t is cosine kx minus omega t plus I sine kx minus omega t. So it consists of real and imaginary parts, which are just a cosine traveling wave and a sine traveling wave. The phase speed, the speed of the crest then, is equal to what? Omega over k. So v phase is just omega divided by k. But it turns out, and again, look at the derivation of this in your book, it turns out that the group speed, if I add a bunch of waves together which have very similar wavelengths, the group speed is d omega dk, whereas the phase speed is just omega over k. Light in a vacuum. What do we call the speed of light in a vacuum? C, right? V phase for light is c. Light of all wavelengths travels the same speed. So it must be that c is omega over k for light waves. Or in other words, omega is c times k for light waves in a vacuum. So V group for light waves in a vacuum is d omega dk, which is c. If omega is ck, then d omega dk is c. So light in a vacuum, the group travels at the same speed as the phases do. But that was that situation where if I perfectly match the speeds of the two waves, then the envelope just marches in lockstep with the wave crests inside of it. That's what happens in light in a vacuum. So if you have this situation, this is the type of relation you get between omega and k for a non-dispersive medium. In a so-called non-dispersive medium, all wavelengths travel the same speed, and so that just says that omega is that speed times k in a non-dispersive medium. But look at quantum mechanics for our free particle. For our free particle here, make sure I do this right here. Should be able to do it off the top of my head, but I don't want to screw myself up here. All right, well, let's look at these guys. For our free particle, we know that E is